Group 15 presents proposal for Sarnia Photovoltaic Power Plant. We will be discussing about the following. First, background, execution analysis, economic analysis, environmental impact, and social impact, and at the end, the conclusion. For the background, Enbridge aimed to launch the world's largest operating solar farm, beaming 80 megawatts of solar power onto Ontario electricity grid from Sarnia. One of the primary motivators of the project was to take the advantage of the Ontario Green Energy Act. For the constraints and requirement, energy was estimating to meet around about 12,800 homes. For methodology, and we'll be talking about different methods we use to determine if the project will be successful with regards to the impact on the community. It was expected that the project will complete in 1.5 years of the time frame. The execution analysis will be taken care of by our project analyst, Mike.
We'll start by defining our project scope. Our objective is to build the most financially and environmentally friendly photovoltaic power plant in the city of Sarnia. Our project constraints for budget should be within 400 million. More on that to be discussed by our economic analyst. The modules must be manufactured in state-of-the-art facilities whose certified management systems are up to date with the latest environmental and technological standards. Finally, the project will be managed and operated by Enbridge, who will contract the construction to First Solar. We'll be using First Solar's Pro and Thin Film PV technology, which has the lowest environmental footprint and the fastest energy payback of current PV technologies. Let's dive deeper into the project specifications. The operational PV plant will have 1.3 million solar modules and a nameplate capacity of 80 megawatt. The facility will spread over 950 to 1,100 acres, containing approximately 635 acres of modules with an annual yield of about 120,000 megawatt-hour emissions-free power. The project will be under Enbridge, but First Solar will be completing its contractual obligations pertaining to the development, engineering, and construction of the overall facility. Let's discuss some details regarding the project team's roles and organization. Enbridge is assuming the role of the project sponsor, providing resources to accomplish our objectives. Naman Gupta will be acting as the project manager and will be responsible for organizing, directing, and planning all the aspects of the project cohesively. As the project management analyst, I'll be interacting with the research department and its analysts, ensuring that project ideologies and methodologies coincide with the project charter and its scope. Under the research head swap, we have Aidan Asser and Naman Jain taking over the environmental, social, and economic analysis respectively. Let's move on to the communication tactics we'll be adopting. Our plan can be divided into two categories, synchronous and asynchronous. We'll conduct live meetings within our individual teams and computer assistance conference calls with the frequency decided by the team lead. Within the team, members are urged to maintain open channels of communication through instant messaging and equipped with our company's cell phones to exchange time-sensitive information. Under the second category, we have emails, Kanban boards, and RSS. Risk management. Our project is directly affected by external factors like political elections, economic trends, technology, and scientific breakthroughs, and most importantly, weather. To keep up to date on all these factors, we'll subscribe to reliable online news sources, and RSS talked about earlier helps facilitate this process. Many of the risks mentioned on the slide can be managed through financial instruments and insurance products. Weather risks can be mitigated through weather futures. However, we do recognize that for relatively young industries like solar, it often means that financial risk management products are badly repurposed from other fields and prohibitively priced.
After the planning phase of the project, Enbridge will review the work given to the First Solar on a weekly basis. Various site visits will be organized throughout the project timeline to make sure that the project goes smoothly. In case if there's any amendments are required during the different phases of the project, enough time is considered during the planning of the Gantt chart.
Let's take a look at some project management tools we'll be using, like work breakdown structures. On this WBS organizing chart, work can be divided into 4 broad categories, with site work which starts from site survey to assembly. The second segment's work packages include acquisition and activities related to obtaining utilities and protection necessary during and after the completion of the facility. The municipal inspector comes and inspects the whole power plant and approves it for production. Finally, First Solar needs to accomplish some site cleanup services that include the handover of the complete project details to Enbridge. On the left, we have the table where we'll identify the activities by separating the work packages listed in the last level of our indented WBS on the right. It's estimated that the project will take approximately 2 years for completion of Phase 1 and Phase 2. The timeline was designed based on the data provided by First Solar and comparing our facility with other solar power plants with similar objectives and specifications. On the chart, we'd like to draw your attention to the electrical and control system installation, which is critical and estimated to take the maximum time. For monitoring, planning, management, and control of our project, we've designed an activity on node or AON representation where each node represents activities. While both AOA and AON are valid representations, we've found the latter to be a more common practice among professionals and an intuitive way of representing our work packages. Through this approach, 2 concurrent activities that start after a common predecessor task is completed is represented by 2 arcs. With the identification of work packages, estimation of duration, and mapping of dependencies completed, we'll use this information to develop a CPM network to identify the critical path of our project. In red is our critical path, a set of tasks that must be completed as planned in order to keep our product on schedule. As expected, the procurement of resources that includes the utility and facility production and the assembly that includes the electrical and control system installation are part of the critical plan. The project analyst and project manager will ensure that these deadlines are strictly met to adhere to the time constraints of the project.
Let's take a look at the economic analysis. In the economic analysis, we'll be taking a look at many different approaches. We'll be using the sensitivity analysis to compare different solutions and to find our true MARR. We'll be using the annual worth method to best visualize the net annual cash flow. We'll be using the future worth method for the ideal case of checking out large-scale projects and consider solar energy despite its inherent inefficiency. We also look at the present worth / payback period, although we will not be presenting it in this presentation, and it will be further discussed in our report. This is because these two methods are not as relevant. Here is some key information on the Sarnia power plant. It will generate electricity for 288 days of the year based on the standard weather patterns in Sarnia. It will be a plant of 80 megawatt AC capacity with 120 megawatt energy generated per year. The government incentive pays us 44 cents per kilowatt hour, while only 8 cents for any other power source that we decide to go with. Different solar panels will be considered as well as their cost in this project. For simplicity, we generalize the innovation structure cost, which would be very difficult to determine ahead of time as it is being off-sourced to First Solar. The MERR for a similar project has been 8%, and this is the number we will initially use. Here's the positive cash flow. We have the energy calculated as the integral of P with respect to time. The total energy is the product of the power capacity and the number of hours in a year. The plant gets 288 days of sunlight, making its capacity to be 0.17. The total energy is about 120 megawatt hour, as calculated. Multiplying that with the government incentive, we get a revenue of about $52 million a year. Salvage value is considered on the last year of the solar panel warranty, and considering the worst case of 0.04 cents per watt, we would have a salvage value of about $3.2 million. Keeping that in mind, these values are rough estimates derived from a previous power plant. The negative cash flow consists of the cost of labor, the equipment, land, and First Solar commission. Labor and equipment cost is averaged using the average cost per watt value. The cost of land is the product of the cost per acre and the number of acres purchased. First Solar is the contracting firm that charges its fees for engineering, innovation, and land excavation. This brings our total to around $210 million. We need to consider the cost of inverters and solar panels separately. We also need to find the O&M cost, which depends on the type of solar panels we want to use. This will be further analyzed in the sensitivity analysis. This is the generic cash flow diagram of our project. As you can see, the ICC is the initial construction cost, the S value is the cost of solar panels, I is the cost of inverters, O&M is the cost of operation and maintenance, P is the profit, and salvage is the salvage value. So what happens here is from year 0, we initially invest all of our money for our initial investment plus the cost of the solar panels and the inverters. At year 1, we start collecting the profit and pay the O&M value up until year 9. Then in year 10, we must pay the O&M as well as the cost of replacement for the inverters, as inverters only last 10 years. Then in year 11 to year N-1, we continue to pay the O&M and collect the profit. Keep in mind though, at year N, which is the last year of our project, this is the year where we collect the salvage value alongside with the profit, and that's when our project ends. Here is a sensitivity analysis and some approaches that we're going to be taking. First one is the time division of the construction costs. Next, we'll be looking at the different types of solar panels to select and finding the MARR. Some possible solutions are spend a lot and have a higher capacity so we get more solar revenue. Another solution is spend less initially, gradually increase capacity over time to reduce high capital requirement. These elements listed below are the different grades of solar panels to select from. And the 3 solar panels below are the 3 main types of solar panels that we will be discussing. Since the capital of solar power plant has proportional costs and proportional revenue associated, it really doesn't matter what capacity size we set for the power plant. Ideally, we want to be as efficient as possible for utilizing the land that we have bought, and we wish to make sure that we achieve maximum throughput. That means that if one inverter can support 10 solar panels and each battery can support 15 solar panels, we should use a common multiple of 3 products to maximize efficiency. That means we should have at least 30 solar panels, 3 inverters, and 2 batteries to make the maximum use of the resources. Lucky for us, we aren't using batteries since the inverters help transfer our electricity appropriately. We will ignore safety margins for overloading for simplicity's sake. We also want to invest as much as possible since innovation and contracting administrative costs are a one-time initial cost, which means that to ask First Solar to take the project again, we must bear the startup costs again, so it is better to associate the maximum workload to them initially. Let's compare different solar panels. The chart on the top shows industry standard solar panel materials. We will compare fixed tilt CSI and CDT. These are 2 different materials. We will compare efficiency, longevity, price, and maintenance cost. We will choose between either polycrystalline and thin film solar panels simply because these 2 panels are the industry standard and are appropriately priced. Don't consider monocrystalline because it has negligible difference in performance from polycrystalline, but it is still more expensive. Thin film is good for Canada because our weather is not very hot. The warranty for thin film is 20 years but may last longer due to the weather of Canada. Thin film is roughly 50 cents per watt, whereas poly is roughly 70 cents per watt. Thus, a thin film is roughly 0.714 times the cost of the poly. Using the model of an existing plant, we know that for 62 kilowatt capacity, poly costs a certain amount, and we can apply the factor to a thin film model accordingly. All in all, the initial cost for thin film is $22 million, and the O&M being $4.2 million a year, whereas polycrystalline has a more expensive initial cost of $31 million, but a cheaper annual cost of $3.8 million a year. Here's a quick summary of all the cash flows with the list on the left for polycrystalline and on the list on the right for thin film. Now let's discuss the present worth versus the payback period and why we will not be using them in our calculations today. While we found that the concrete value of these methods in our report, we decided not to display those here as they are considered irrelevant. Present worth helps determine the company's evaluation in the modern day market. Since this is a long-term project and Enbridge does not wish to sell its shares, we will ignore this case. The payback period discriminates against long-term projects as it does not take into consideration the value of money over time and is a preferred method by companies that struggle raising capital. Since Enbridge has a net income of $50 billion, we do not need to worry about initial capital. True profit appears over a long period of time. We will use annual worth since it's easy to visualize and allows Enbridge to determine if the government incentive is sufficient for the project to be profitable. We prefer this method because it helps us better prepare budgets for other projects and shows us that our company is in positive cash flow. On the left, we have broken down the annual worth. It's the sum of the annual benefits minus the annual disbenefits. The annual worth calculations. Taking our cash flow values and converting them into annual worth, we find that the polycrystalline has an annual worth of about $24.5 million, whereas the thin film project will have an annual worth of about $23.2 million. Since the difference is very low, we may need to pick a project over the other after conducting a future worth analysis. Finding the optimal MARR. Since we found our annual worth calculations to yield very large values, we should try and find the true MARR such that we approach a $0 annual worth. Here is a graph of the MARR versus the annual worth. It seems that the truly optimal MARR is around 18.66%, which we found using the line best fit estimate. We'll use this number for our future value calculations. Now let's look at the future value comparison. Future worth is the future worth of benefits minus the future worth of disbenefits. This is a neat method to compare our solutions because solar energy is notorious for paying back after a long period of time because of its inherent inefficiency. Since polycrystalline has a longer life than the thin film, we must find the lowest common multiple between the two project life cycles. Thus, we set T to equal 100. We also consider that the foundation cost over the many years has negligible costs associated with it, since the major costs are solar panels and inverter replacements. Using the equations that we found in the future worth of polycrystalline is about 2.5 times 10 to the power 14, and the thin film is 4.15 times 10 to the power 14. These are massive values, but that is expected since this is an evaluation of a project over 100 years. Thus, in conclusion, we should pick thin film since its future worth is 1.66 times better than polycrystalline. Let's summarize what we learned. From the annual worth analysis, we can pick either projects. From the future worth analysis, we should pick the thin film project. Due to the nature of rough estimates, it may actually cost more for reconstruction of the power plant after a certain period of time. We pick thin film for its future worth, and its ability to be cheaper with larger purchases. Its low upfront cost makes its repair affordable in cases of a disaster, and land in Sarnia is cheap, so the thin film panel's disadvantage of occupying large areas is not considered. Time division of construction cost. We can break our construction into phases, or we can invest all of our money up front. We have the option of breaking our construction costs in half by investing the second half of the investment in year one. Using the 18.66 MARR, we can find the annual worth of the thin film project to be around 1.6 million. Now we just got to compare it to splitting the initial investment. This is the cash flow diagram of the two different investments, which is the first half of the investment, which is put into place at year 0, and the second half of the investment, which is put into place starting at year 1. As you can see, the diagrams are very similar to our original generic cash flow diagram, with the exception that there are two different diagrams presented here in such a way that the first half of the investment stops at year 20, whereas the second half of the investment starts at year 1 and ends at year 21. When we sum these two cash flow diagrams together, we have the sum of the cash flows, and this is the diagram we create. We can use the annual worth comparison with the full capacity, and we have broken it down to two sets of calculations. For the first half of the investment, we found that the annual worth is a negative 150,000. Whereas for the second half of the investment, the value turned out to be negative 82 million, which is quite a large sum. Therefore, in the total annual worth comparison, we found that it is better to operate at full capacity, as it has a greater annual worth value.
So moving on to our environmental analysis, we talk about the negative repercussions on the environment from having to use 950 acres of land and how to mitigate them. Some of the repercussions are the removal of local plant life from the ecosystem, the increased wildlife interactions from having to interact with the wildlife that used to inhabit the land we're now building our power plant on, as well as any heavy metals that may be polluted into the environment through the construction of our solar panels.
One of the major problems that Enbridge is facing is that a utility-scale photovoltaic plant can drastically impact their surrounding environments. Enbridge came up with a solution to this, which is their neutral footprint plan, which ensures that the land and environment in and around our projects are protected and improved. Under this plan, Enbridge's goal is to maintain the environmental footprint at January 2009 levels by taking the following actions. The neutral footprint plan has three key ideas that will be implemented. The first is that Enbridge will plant a tree for every tree that they have removed in order to build new facilities, conserving an acre for every acre of natural habitat that the company impacts, as well as generating a kilowatt hour of renewable energy for every kilowatt hour of energy its operations have consumed since January of 2009. The plant uses thin film cadmium telluride photovoltaic technology. This technology has one of the lowest environmental impacts of any photovoltaic technology out there right now. This means that the technology can be easily scaled up and still have a relatively low impact on the environment. This technology also has the fastest energy payback of the current photovoltaic technologies out there. Deciding on this technology allows Enbridge to meet their various goals that they committed to achieving within this project. Another major issue that Enbridge is facing is that the heavy metals that they use have potential to pollute the environment and affect the health of workers. Enbridge ensures that they are efficiently using the heavy metals such as cadmium within their project. This ensures that only 1% of cadmium is wasted, which can be easily recollected and utilized again. They have also put forth other precautions such as the insulation of heavy metals between glass, which protects the heavy metals from escaping into the environment. Workers are also scheduled for regular blood and urine tests in order to check for their cadmium exposure levels. One other major issue that Enbridge is facing is how they will mitigate the solar plant's effects on the local plants and wildlife. Enbridge will begin by removing invasive species in the land that the solar plant occupies, which are called phragmites. Phragmites outcompete the local plant life and are a very poor source of food. The phragmites would then be replaced with the seeds of local plants for a better and more sustainable environment. Regarding the wildlife, Enbridge will implement a synthetic urine that is not harmful to the plants, but will repel certain animals such as birds and raccoons, which will prevent animal damage. Then, over time, as the plants grow, the replaced local plant life will provide the local wildlife with more food and a more familiar habitat. Enbridge has also partnered with Return the Landscape, which ensures that Enbridge will spend $100,000 restoring the habitat in surrounding areas over the course of the next 5 years.
So now finally, we're now at the social analysis, and the main problem for this section of my answer is the solar power plant that we're going to build going to be a good or a bad addition to the community, both in the long run and the short run.
Now, let's talk about the social impact this project had on the Sarnia region. In terms of jobs, it employed about 800 workers and provided indirect benefits to several businesses in the region and sourced materials locally wherever possible. The farm currently employs 2 full-time employees. As of its completion, it provides an excellent field trip destination for the local school children to learn more about renewable energy and electricity generation. Lack of information in regards to community opinion of a solar farm taking up space in their city suggests residents were not opposed to its construction. This isn't to say no one had issues with it, but there was no significant recorded opposition to the project. On the contrary, articles suggest people were excited about the development and more concerned with its ability to produce power and whether it could outweigh its cost in generation. The project did advance the Ontario Green Energy Act in producing jobs and economic growth in the province, which can be considered a net positive social impact, on top of placing Sarnia on the map as the location of one of the world's largest solar farms at the time. So those are some of the pros with building the plant. Now let's talk about some of the cons. During the construction of the plant, residents of Sarnia may hear noise of vehicles and excavation tools. While the plant is being constructed on the outskirts of the city, and most residents won't be affected, there will still be a few areas that will be. On top of that, there will likely be more vehicles moving through the city itself to transport materials, or when workers want to go on break. Looking into the future, this could also change how Sarnia's city layout will need to be constructed, as newer buildings and areas might become some way separated from the rest of the city, just because of the land space the plant takes. This could mean splitting access to businesses for residents on one side of the farm or the other, or the need for another school so that children don't have to travel too far to get to one. On the flip side, the workers would also have to travel quite far to reach on-site activities, as the city is located a ways off from any major US or Canadian city. This could also mean materials transport and daily worker commute could be more difficult, especially during the winter months.
And so we're now at the closing thoughts of our presentation. So through our economic analyses, we found that thin film solar cell is the best economic choice in terms of what solar cell to make in our solar power plant. And to look at our solar power plant as a whole, we found that even though we have a high construction cost and recurring maintenance costs on these solar panels as we seek to replace them, we do generate a very high annual worth from the electricity that we do generate, as well as we get the occasional revenue from salvaging some of the precious metal from the solar cells as we seek to replace them. So in conclusion, yes, the economic analysis sees that building this power plant is something that is worthwhile to do. Moving forward to our environmental analysis, we found that we could have potentially very negative effects on the environment, such as displacing local wildlife species, as well as polluting the environment and taking up such an amount of land from local plant life. But through our actions of trying to have a positive relationship with the local wildlife and local plant life in the area, as well as our efficient manufacturing processes that protect the environment from pollution, we find that it is actually worthwhile to build this power plant from an environmental perspective. So now we move on to the last analysis, which is the social analysis. And the problem we wanted to determine was, at the end of the day, do we have a good or a bad relationship with the city of Sarnia? And during the construction phase, it's mixed because we have increased traffic and increased noise pollution from the construction itself, but we do employ 800 workers. But what really answers our question is in the long term, where we see that the power plant is a great location for local school children to come and learn about their local community as well as power generation. And obviously, with a power plant, the amount of clean electricity that we produce is enough to power the entire town, which by itself is a huge plus to the relationship. And we find that through these benefits, that we end up with a positive relationship with the town in the long run. So wrapping things up, we've taken a look at three analysis methods: the economic, environmental, and social analysis, and we find that all three produce a positive result, and that because of the profit determined from our economic analysis, because of the mitigated environmental costs from our environmental analysis, and because of the long-term positive relationship with the town for our social analysis, that overall is worthwhile to build the power plant that we seek to build.